So far, we have finished all the needed elements to understand quantum computing and how to do computations with a quantum computer, from the quantum register to the design of the quantum circuits to the understanding of the action of the quantum gates, and of course, the measurement, which can happen totally or partially. Now we'll move to an example of this, a simple quantum algorithm, and yet it is very powerful and it has a lot of mystery and a lot of physical euphoria in it, which is a quantum entanglement. The quantum entanglement is a phenomenon where two or more qubits are correlated in the measurement in such ways that the state of one qubit is dependent on the state of the other qubit. So, in a nutshell, if you have two qubits and you measure one, the measurement of one is correlated to the measurement of the other because the description or the quantum state of one qubit cannot be described independently from the other qubit. And for that sense, the quantum entanglement would give you something for free. So if you measure a first qubit, it gives you a clue about the measurement outcome of the second qubit for free. From a mathematical perspective, you cannot defactorize, and back to the original state. And from physical perspective, there is measurement correlation. We are going to see this now. So one of the examples, we can have the Bell state. The Bell state is an entangled state. So why it is an entangled state? We are going to see this shortly. Entanglement is very essential for quantum computing. It's also a very fundamental property in quantum mechanics, which has no classical counterpart. It is very important in quantum computing because it's also used to protect the qubits. If you entangle several qubits together, there is some sort of protection, and you would know immediately if one qubit had an error or so. You would spot this immediately via the entanglement process. Now let's come to this particular example. We have the action of two Hadamard gate can give us a state, which we have seen in earlier videos, which is composed of half ket 00, half ket 01, half ket 10, half ket 11. Now let's make a trace table of the two qubits which are involved here. We have the first qubit and the second qubit. So this is the first, this is the second, and this is our trace table for the states of the qubit A and B, which they are expressed together with the state psi. Now in the first column we see the qubit A, here we see the qubit B, and here we see the state psi, the component of the state of the component of the state psi. We have, of course, 4 possible states because we have 2 to the power n again, and n is 2 qubit. So we have 2 to the power n, which is 4 possible states for the 2 qubits A and B. So the total system will be composed of 4 possible states or 4 possible configurations or 4 possible situations. The first situation is where both qubits are in zeros. So this is denoted as ket 00. So we have qubit A as 0, qubit B as 0. The second situation where we have the first qubit is 0 and the qubit B, the second qubit is 1. So we have ket 01. Third situation is A is 1, B is 0, and this is denoted as ket 10. And the fourth situation or the fourth state is 1, 1, where the two qubits are 1, 1. So far, so good. This is the analysis of what we do to the state vector representation of the state psi. Now let's have a look on the states of qubit B when A is in the same state 0. When A in the same state 0, which is colored here as red, B in a superposition. So when state A is in 0, B is still in a superposition, which means that if you make a partial measurement and you find A to be 0, the other half where A is 1 will disappear because it now has collapsed. So we have a partial measurement, partial collapse for the quantum state. Then A will be in definitive state and B will stay in the superposition between 0 and 1. Similarly, if we look at when the state A is in 1, then we still find the qubit B in a superposition. This part will disappear, and then we have a part where the qubit B in a superposition of 0 and 1. So with this, we have the full spanning of the Hilbert space of these two qubits. Okay, so what the entanglement will do? Let's have a look to the following circuit. This circuit is what produces the entanglement. We have the Hadamard gate acts on the first qubit, and then we have a CNOT gate, which has the first qubit as a control qubit, and then the second qubit as a target qubit. Mathematically, we can see it as the following. First, we act with the Hadamard gate on the first qubit, so the second will have an identity acting on the qubit which are initialized in 0, 0. Then we are gonna have this action which will happen to the first qubit. The identity will do nothing to the second. So we are gonna have 1 over root square of 2, get 0 plus get 1, tensor product, get 0. So this will give us 1 over root square of 2, get 0, 0, plus get 1, 0. Now this is the action. You can work out the tensor. This is one of the tensor properties. You can also check it in the linear algebra course. But let's take it for granted. You distribute this here and there. So you end up having two situations or two states. Now let's act with the CNOT gate. The CNOT gate, which takes the first qubit as a control, second as a target. This one will act on this new state. Then what we're gonna have here is applying the CNOT gate. So the CNOT gate is a conditional gate, so it looks on the control qubit to decide the action that will be done on the target qubit. In our case here, if we look on the first qubit, it is 0, then the decision will be taken. If the first qubit is 0, don't do anything to the second qubit. So the second qubit will stay the same, 0. Then we go to the second gate, the second state, then it looks to the first qubit. Is it 0 or 1? If it is 1, apply the action of the X gate on the second qubit. So it's now 1, so I apply the action, then the action of the X gate will be to reverse the second qubit from 0 to be 1. So I end up having 2 1s here. So this is what we have. We have now produced one of the Bell states or an entangled state, maximally actually entangled state. We can arrive to similar states, of course varies slightly, which are entangled as well by varying the input state, by varying the initialized qubit state. So for example, based on the inputs or the input states of qubit A and B, the output states of qubits A and B are given here. So if both two qubits are zeros, then the action of the Hadamard on the first qubit followed by the action of the CNOT gate where the first qubit is control, the second qubit is the target, will be 1 over root square of 2 ket 0, 0 plus ket 1, 1. Similarly, if the first qubit is initialized to 0, the second is 1, then we are going to have ket 0, 1 plus ket 1, 1 times 1 over root square of 2. If A is 1, B is 0, then we are going to have 1 over root square of 2, ket 0, 0 minus ket 1, 1. If both are 1s, then we are going to have 1 over root square of 2, ket 0, 1 minus ket 1, 0. So those are the possible entangled states or Bell states. Those are the states. We call them Bell states, and we have ket B0, 0, ket B0, 1, ket 1, 0, ket 1, 1, and these subscripts denote the initialization of the quantum register before applying the Hadamard gate followed by the CNOT gate. Here we see it in the matrix notation. You can work out this matrix. If you apply the Hadamard, then the Hadamard will be multiplied tensorically with identity to have the action on the first qubit, and then this will be the result. You will get a superposition of this situation, and here we can see the entanglement. How it can even be, because if you go here, if you measure partially the first qubit, 0, you will know for sure that the second qubit is 0, because this is we have only one situation or one state where both of them are zeros. So you get something for free. If you measure the first to be 1, then the second will be 1 as well, because you know that this is the only situation where both qubits are in one state. If we come to a given state, not normalized, which has the following, then here if you measure the first qubit to be 0, then you know for sure the second qubit is 0, because this is the only situation where both qubits are zeros. But if you measure the first to be 1, you don't get any free information, because the second qubit still you can have two situations where the second qubit could be 0 or could be 1. So the entanglement here existing partially as well. Okay, so this is the meaning of the entanglement. You can get this by working out or tracing what information you can get on the second qubit for free if you do. If you get all for free, then this maximally entangled state, you can get it partially like this situation. So there is partial entanglement here. Of course, with the density matrix, we can correlate, we can know the entanglement degree, and we can work this mathematically by having the following. You can act with Hadamard gate. We have now Q0, we have Q1, Hadamard gate, followed by the CNOT gate. And then we can work this mathematically by applying the Hadamard identity on the second. And after we finish, we get here 1 over root square of 2. Then we can apply the CNOT gate, and this is the CNOT gate. it could be applied on this one, and then we get the results. And this way of multiplying matrices is actually what is done on a computer in a state vector simulation in the exact way. Of course, there is other methods to do using matrix product states or different ways of multiplying the tensors, much more efficient ways. You can check our development in Julia package concerning the simulation of the qubits using Big Endian and the Little Endian. With that, I have outlined to you how to do quantum computations just from the basic scratch until you apply the entanglement, very simple algorithm of the entanglement, and you can run it on an actual quantum hardware. I also discussed the physical principles behind every step in the quantum computing paradigm. We need to think about the quantum computation in a way that how to initialize the qubit. So we create sort of a quantum bubble. We manipulate this quantum bubble or the quantum box to do certain operations. We cannot look at it because otherwise the state function will collapse. And from that, we retrieve the information from the quantum system via the measurement. And then we need to make post-processing on this by correlating the outcome of this measurement to the values that we are looking for in our problem or the solutions that we are looking for. So we discuss the workflow, the procedure, and how to run quantum algorithms. If you have questions or you have comments, please leave them in the section of the comments below or send them directly to me on LinkedIn or any other platform, and I will be happy to address them. Until then, let's meet in future videos and future courses, and let me know if you have specific wishes about the upcoming courses. If you need anything, please visit our page and our channel iCafe and my personal channel in English, and also I have another one in Arabic.